Okay, lecture 14. So this is where I start to try and introduce momentum conservation. So this is quite a tricky concept to get across. So I'm going to do it twice in the module. So we're going to do it now and to try and get the main idea across. And I'm going to do it again next term. So one of the reasons I'm doing it now is the next 3 lectures you've got are statics, and what I want you to do is to view the statics problem as a simple case of the conservation of momentum equation, and we'll come to that towards the end of this lecture. The other reason I wanted to do it is I wanted to do it immediately after defining the mass conservation equation, because I can use the mass conservation equation derivation as an analogy for what we're trying to do with momentum conservation. Okay, so we're going to do the same thing. We're going to use the Reynolds Transport Theorem. I'm going to try and explain where this comes from and why it's happening, and then I will provide some more simple momentum equations that you're going to use primarily, and in the lecture I will give you some examples, and you will have a write-up of these for you to download from Blackboard. Okay, so just to sort of try and set the scene a little bit, when we're using the Reynolds Transport Theorem, we take a variable, an extensive variable, in the Lagrangian frame, and we write an Eulerian conservation equation for the intensive version of it. So we did this in the previous lecture for mass. So mass is an extensive variable, and we defined the Reynolds Transport Theorem for its intensive equivalent, which is density. So we're going to do the same thing for our 2 other remaining variables that we're interested in, momentum and energy. So we're dealing with momentum today. So momentum is an extensive variable, so how much momentum you have depends on how much mass is there, and it has an intensive equivalent, velocity. So when we're talking about the velocity field in fluid mechanics, effectively what we're saying is this is the momentum distribution in my fluid per unit mass. Okay, and one of the reasons we're sort of doing this incrementally is when we did it for mass, it's a scalar quantity, and you can go from a Lagrangian equation to an Eulerian equation with a scalar quantity, and it's sort of conceptually easy to follow. When we start talking about momentum and converting it to, so Lagrangian momentum and converting it to Eulerian momentum, it's a bit more difficult, because momentum, if you remember, is a vector. So when we write an equation for momentum, we actually have to write 3 equations, one for the x direction, momentum conservation, one for the y, and one for the z equation. Okay, so this is why we did mass conservation to start with, to try and understand, to give us a handle on what we're trying to do, to get momentum conservation understood. Okay, so just to sort of set the scene, this is what we did in the previous lecture. So we have a control volume, we have a small amount of area, and we want to think about mass conservation, and we ended up saying that this is the velocity vector coming out of some point, and this is the unit normal coming out of that point, and the mass flux on this particular area is due to the normal component of that velocity. So we've got the velocity in this direction, and we want the component of that vector in this particular direction, and it's the normal component of the velocity that contributes to the mass flow. Okay, and the other way I want you to try and think about this, and is in the general sense, in that I want you to think about the velocity field as carrying information. And in particular, I want you to imagine that I've got some information here and my velocity field is carrying this stuff into the control volume, and then it tracks across the control volume, and then my velocity field carries this information out of the control volume. So in this particular example, density is my stuff, my information that I'm transporting with my velocity field. Okay, and so when I write my conservation of mass equation, effectively I'm saying that the same amount of density is flowing into my control volume as there is flowing out, and that must balance because it's a conservation of mass equation, so the sum of this particular integral must be equal to 0. Okay, so what I want you to get across the idea that the velocity field is transporting or conveying information. It can convey anything. It can convey density, it can convey energy, and in this particular case it can also convey momentum. So we know what the Lagrangian fundamental equation for momentum conservation is. It's Newton's second law, force is equal to mass times acceleration. So what this equation really is a rate of momentum change equation. So mass times acceleration is the same as m du by dt. So effectively, my right hand side of Newton's second law is the rate of change of momentum, and that rate of change of momentum is caused by the force that I apply to this object in the Lagrangian frame. So if you can imagine, we have an apple and it starts falling from a tree. So it's not moving to start with, so there's no drag, but the gravity forces are acting, so the apple starts to speed up, it accelerates, and as it accelerates, the drag force on the apple increases, and we get to a point where the gravitational force and the drag force are equal, and at that point the apple gets to its terminal velocity and it doesn't go any faster, and the rate of change of momentum is 0, and you end up with two forces on the left hand side and a 0 on the right hand side. Okay. So the other thing we can do is we can say, well, we can apply the Reynolds Transport Theorem to Newton's second law, just in the same way that we applied it to the mass conservation equation in the previous example. So I've got my this is my rate of change of Lagrangian axial, my rate of change of Lagrangian momentum, and that's equal to the force that's being applied to this particular object, and then I just apply my Reynolds Transport Theorem to how my momentum changes with respect to the Eulerian frame. So this is, if you like, a box that the apple might flow through. Okay, and we've got two terms here. So effectively what we've done, I've used my intensive version of momentum, which is my velocity, in the same way that I did for density for my mass conservation equation. So this is the general momentum equation that Part 3 and Part 4 MSc students and PhD students use. And there are a number of different forces that we apply to make that depend on the problem. So for instance, you might have pressure forces, you might have gravitational forces, you might have viscous forces, and all of these things add to create a sort of a net force on the control volume that impacts the total momentum change in the control volume. Okay, so this is a little bit different to mass conservation, we can have a little bit of momentum flowing into a control volume and a lot of momentum flowing out of that control volume. And there therefore must be a force on this control volume that keeps it stationary in space. So, and this force on the control volume that keeps it stationary in space is usually what we're after. So if you can imagine a jet engine that's under test and it's bolted to the ground, and you run your jet engine, so you have cold air going in, has a little bit of momentum going in, not very much, and then you pressurize it and you inject lots of fuel, you get lots of high temperature, high momentum exhaust coming out the back of the jet engine. And if you think of your jet engine as a control volume, there is a net force on that jet engine. There is a net force on the support connecting the jet engine to the ground. Okay, so this is the same way. So this is why the sort of the momentum balance over a control volume, based on the net flux or the net flow of momentum into the control volume, doesn't have to sum to zero. Okay, so this is a little bit different to mass conservation. So the Reynolds Transport Theorem is great. It allows us to define these things without getting into all of the details, or at least we only have to get into all the details once. But it doesn't really help us understand where this thing comes from. So let's have a little bit more of a look at my net flux of momentum going into this control volume. So I'm going to try and do this by analogy. So we started off by saying the flow field carries information, and we can use the sort of the conceptually simple concept of the velocity field carrying density. So there's mass, so that's mass per unit volume, density, going into the control volume, and there's mass per unit volume going out of the control volume, and the net mass flux across the control volume must be equal to 0, and that's how we get our mass conservation equation. Okay, so we can do the same thing and just change the thing that is being convected. So we can define an elemental momentum flux through our little teeny tiny area dA. Okay, so we still got our velocity field here, this u, and we're saying, well, our velocity field can carry some momentum. And it's the same as in mass conservation, in the sense that only the normal component of my my mass conservation contributes to carrying momentum. Okay, so if this is the velocity field, only this component of the velocity field can carry any stuff. So in mass conservation it's density, in momentum conservation it's momentum. Okay, and so effectively we can have a momentum flux, so that's the, if you like, the momentum per unit area, defined for this little teeny tiny area. And it's quite interesting to look at, and if we do define this in the same way that we define the mass conservation, here's our momentum, and here's our normal to the area, and this is the thing that's carrying some momentum out of the control volume at this particular point. Okay, and if you had your area on the other side pointing out this way, you'd have some momentum being carried into the control volume on this side, and you'd have the opposite sign on this thing. Okay, so this is my momentum, and if we check our units here, we've got the density, which is this thing, and then we've got area, which is this thing, and we've got a velocity here, and we've got a velocity here. So this is 2 meters per second, so that's what we've got here. If we go through and work all of this out, we find out that this thing is newtons. So effectively, when you have momentum flowing into or out of a control volume, it's actually a force balance on this surface. So hopefully you can understand why this is a momentum balance, because this flow of momentum in and out of a control volume is actually creating a force on this surface. And like a jet engine, you have a small amount of force on the inlet and you have a lot of force on the exit of a jet engine, so you have an imbalance of force on the control volume. And in the example of a stationary jet engine that's bolted onto the ground, there is a force on the support of the jet engines on the ground that's holding this jet engine stationary when you switch it on. If it wasn't there and you switch the engine on, it would start to fly off. Okay. The other thing to note is that here what we've done is we've defined momentum in the x direction, and so you can and the difficult thing is you've got a velocity here and you've got a velocity here, but I want you to try and imagine that this velocity and this velocity are kind of two completely different things, really. So this u dot n is the thing that's carrying information, and this rho ux is the information in the same way that this rho is the information up here. Okay, so in this particular case I'm saying that there's some axial momentum that's being carried through the control volume surface on this location by this velocity field. Okay, and I could say, well, I want to do the same thing for the y momentum or the z momentum, and I effectively write two different versions of this equation to say this is my momentum being carried in the x or the y or the z direction at this location by this single velocity field. Okay, so this is quite difficult to get your head around, and the best way to do it is to try and do some problems. Okay, so what have we got here? So this is my general momentum equation, and mostly in this module we're not going to deal with unsteady momentum problems. So our momentum equation that we're interested in is basically these two terms here. Okay, so this is the net flux of momentum in or out of my control volume, and this is the net force that acts on my control volume. And this might come from a range of different things. Might be the pressure gradient, might be gravitational acceleration, might be viscous forces, and it might be some other stuff that we're not going to deal with. Okay. So similar to our lecture on mass conservation, most of the next term we will deal with inviscid flows, and if if the velocity going into a control volume surface is constant, we can make a simplification to our momentum. So our momentum at a particular point is effectively rho times the velocity squared times the area, and it's often much easier to talk about it in terms of a mass flow multiplied by the velocity at that particular point. Okay, and if we can do that, we end up with a simplified version like this, and we can usually, if we've got one inlet and one outlet, there's the same amount of mass flowing in and out due to mass conservation, and we can simplify our momentum equation like this. Okay, so so this is all that's required for momentum conservation. The tricky bit for understanding how to solve problems is really where to put the control volume and how you apply your additional forces on the surface of your control volume. Okay, so these might be pressure forces, the best way to do this is using an example. And this also sets us up for the statics part of the module, in the sense that you can think of the statics problem. So this is what's the force distribution in a fluid, assuming it's stationary. So effectively, our momentum equation simplifies to the sum of all the forces must be equal to 0. And they must be equal to 0 because our fluid isn't moving. And there are two forces that are present in statics problems. One is the weight of the fluid, and the other one is the force on surfaces that are enclosing this fluid. So a classic example is a dam, and you have the water behind the dam, and the weight of the water creates a stress on the surface of the dam, and you need to be able to work out what that stress distribution is to make sure that the dam is stable. So this is what you will start next week. Okay, so we have worked out how to deal with mass and momentum conservation. We've come across simple forms of momentum conservation, and there will be some examples that I will provide that show you how to do these kind of calculations, and in particular how to work out where the best place is to put a control volume. Okay, thank you.